In this video and the next few videos in this playlist, you will learn a smattering of ideas from generally what is the first unit of derivatives in a calculus course. And so it starts out with this one right here. We have a question that is telling us to determine if f of x is differentiable at x equals 2. And here is the function. So here's the function, and what this is basically asking us to do is see if the derivative when x equals 2 gives us the same slope of the function as this function when x equals 2. If we get the same derivative value or the same slope and when x equals 2 for both of these, then it is differentiable. If not, then the derivative, rather f of x is not differentiable at x equals 2. And so we can take the derivative of this function. And I'm skipping some details here, but essentially what happens is if you use the power rule here and the power rule here, we can get the derivative of this function, f prime of x, is either 2x or 5. And this is when x is greater than or equal to 2, and this is when x is less than 2. So now if we just take these values and substitute them, oh, there are no x's down here, but if we take these values and substitute them in for x, then we can determine the derivative values at 2. So when we substitute 2 in here, we get 4. And if we substitute 2 in here, which again, there are no x's, we get 5. So to the right of 2, we get f of 2 equals 4. Sorry, f prime of 2 equals 4. And to the left of 2, we get f prime of 2 equals 5. And really, since we are unable to mathematically substitute 2 into this function because it's only what happens when x is less than 2, we really are looking at the limit of this as x approaches 5, or as x approaches 2 from the left, but we still get the answer of 5 here. So we're technically looking at limits, but it's a lot easier to understand when you're looking at the direct substitution. So since these are different values, we have 4 and 5, then the original function is not, and that's the important word here, not differentiable. We'll say at x equals 2. A bionic person runs an 80-meter dash in such a way that the distance s run after t seconds is given by this function. The goal here is to find the runner's velocity when he or she finishes. All right, so since we're asking about velocity, we're being asked about velocity, with this function here, this being the position function, if we just take the derivative of the position function, that will give us the velocity. So we can say by the power rule here, this is 1/2 t plus 6. Well, I mean, it doesn't tell us what time the runner finished, right? It just asks what is the velocity when he or she finishes. Okay, so we have to go back and do a little bit of work off to the side like this. So in order to find the time, we need to take the position function, and we know way back up here that the race is 80 meters long. So the position gets replaced with 80, subtract 80 from both sides of the equation. I then multiply everything by 4 so that I am not dealing with fractions in case I need to either factor or use the quadratic formula. And yes, in this case, the quadratic formula needs to be used. And when you use the quadratic formula, you get roughly 9.54 seconds. That's how long it took for this bionic person to run an 80-meter dash. So then we take this value and we substitute it in for t over here so we can figure out how fast the bionic person was running. So when you substitute this value in here for t, take half of that, that's roughly 4.77 plus 6, 4 and 6 is 10.77 meters per second. For this particular function, we are asked to do two things here. The first of which is find the equation of a tangent line to the graph of f of x at the point 2, f of 2. So to do that, we need to first find the derivative so we can find out what the slope of the function is at this particular point. So if we just use the power rule, first we can just look up here and use the power rule to find that f prime of x is 3x squared minus 2x minus 5. So now here we can tell what the slope of the function is when x equals 2 if we just substitute 2 in for these x's here. And when you do that, you get a value of 3. So we substituted 2 into the derivative to get 3, and that is the slope of the tangent line. Now we can just use the point slope formula. Oh, no, we can't. We have f of 2 up here. So as long as we can find out what f of 2 is, again, that's the original function, then we can then use the point slope form. So f of 2 would be 2 cubed minus 2 squared minus 5 times 2 minus 1. This gives a value of negative 7. So f of 2 is negative 7. This is my y value. So now I can create the line. I'm going to do that in this blue color here. This would be y plus 7 as we take the opposite of this when we use point slope equals the slope of the tangent line times x minus 2, and that value was given to us up here. So here is the equation of the tangent line when we are at the point 2, comma, and this we can interpret as negative 7. For part B, it's asking to find all the points on this function. Points is a keyword here, so we're looking for ordered pairs, at which tangent lines are parallel to this line. So now we don't have this ability anymore where we can take an x value and substitute it into the derivative to get a slope. We don't know the x values. It's asking us to find the x values. When we're trying to find points, we need to find the x values. So what we can do then, in order to figure it out, is first we need to look at this equation, negative 3x plus y equals 5. And we need to solve that for y. And the entire point of solving it for y is to be able to pick out this number right here. This is the slope. As long as we know the slope that we're after, then we can start finding x values. Because when you find a derivative, there are two things you can do with it. We can either substitute in a value in for all the x's and generate slopes of tangent lines, or we can take the derivative and set it equal to this slope here. Then that will allow us to find x values, the x values that will generate a slope of 3. Well, I don't know if this will be a shock to you guys, but we already found an answer for this question right up here. We know an x value of 2 will give us a slope of 3. But to run through the whole process here, we would have to solve this equation. So you can subtract 3 from both sides to get minus 8 over here on the left. You can factor this here to equal to 0. And then we can set each of these equal to 0 to get two x values. It would be x equals 2 and x equals negative 4 over 3. Then in order to find the corresponding y values, right, because we're looking for points on the function. That's up here, the original function. So we would have to take 2, substitute it back up here. That would give us -7. We did that already right here. So we would have an ordered pair of 2, -7. That's one answer. And if you take -4/3 and put it back up here into this equation, you'll see that y is 41 over 27. For this example, we have a particle that is moving along the x-axis. At time t seconds, the position is this. So I am almost positive there will be some sort of velocity question here. Here it is. Yes, the instantaneous velocity. This just means find the velocity function using the derivative and substitute in the subsequent value here. So the velocity function v of t is 3t squared minus 4t plus 1, which means then we can just substitute this. This is the derivative of the position function. And then we can just substitute 2 in for that and get, let's see, 3 times 2 squared minus 4 times 2 plus 1. That's 12 minus 8 is 4 plus 1 is 5. And we'll use this units per second. Part B, it asks to find t, so the instantaneous velocity is 0. So again, I already know that this means find the derivative, and in this case, this is much like the last example we did. When the instantaneous velocity is 0, we don't know the time. So when I write out the function like this, 3t squared minus 4t plus 1, we don't know the times. We need to solve for the times. So it's a good thing they told us that the velocity is 0. That way we have a number to put here and start solving for t. You can factor this quadratic expression here. It becomes 3t minus 1 times t minus 1 equals 0. And we have the following times here. The time will be 1/3 seconds, and the time could also be 1 second. And so these are the answers here. And I want to make a note. I'm just going to say it. I will not write it. But if you go through and set a velocity function equal to 0, or you set a position function equal to 0, and you solve for t, and you get a negative value, you cannot use that answer in the real world. Time can't be negative. So we throw any negative time values away. Just be careful of that if you are working on different, I call them physics problems in a calculus course. Last slide for this video, we need to find the equation of a tangent line to the graph of this at the point corresponding to x equals 1. So I'm going to approach this one a little bit differently. I know that we are looking for the equation of a tangent line, as it states here. And in order to find the equation of a tangent line, I have to have a point on that tangent line. And right now I only have this x value. So I'm going to go ahead and substitute this x value in here for these x's and get the y value, so I have an entire point. So if I substitute 1 in for x, then I get back 2. So now this corresponds to the ordered pair of 1, 2. Now that we have an ordered pair, we can go through and find the derivative of this function. So f prime of x will be what's in the denominator. Since there is a quotient here, I will do what's in the denominator, and I'm going to think of that square root of x as x to the 1/2 times the derivative of what's in the numerator, x cubed plus 1, minus the numerator times the derivative of the denominator, and that is x to the 1/2, all over the denominator squared. And if you square the square root of x, you just get x. So this is not quite the derivative yet. This is the quotient rule. However, I have not found these little derivatives here. So I'm just going to write this step out off screen so you can see what the final derivative will look like. So here is the derivative completely worked out down here. Oops. There we go. That's the derivative. Now we need to substitute 1 into this derivative so we can find the slope of the function at that point, i.e., or in other words, the slope of the tangent line at this x value. So if you just go through and substitute 1 in here and here and here and here and here, it makes it a pretty easy calculation because this, I mean, when you're dividing by 1, you're not really doing anything to this function value. So here we will have 1 times 4 is 4, and I'm going to write this down just to make sure I don't goof up. And then here, if I substitute 1 in, I'll have a 2 times 1/2. So I'll have 4 minus 1, which means my slope of the tangent line, or the slope of the function at that point, will be 3. And now I can make the equation of this line to be y minus 2, that comes from up here, equals 3 times x minus 1. Again, that 1 here comes from the ordered pair we found earlier. So this is the slope, or rather the equation of the line tangent to this graph at the point corresponding to x equals 1.